Okay, so what we want to speak about today is the simplex method, the simplex method, and we are going to slowly look into the details of the method. And again, remember when I solved the one of the LPs by using the Excel, when I used the what was that the tool? I checked simplex. Remember, I checked simplex to solve the problem, and this is the method that we want to describe now. The first thing I want to do is give you sort of graphically what simplex does. So that's going to give you some intuition about how the simplex method works. Okay, so first of all, I'm going to give you a graphical view of, so what's the graphical view of the simplex method. And let me explain this by using the same example we used at the beginning. Okay, so remember this was this feasible region that I have. This feasible region, I think what was the objective function here? I think the objective function was 3x1 plus 5x2, and then I think the constraints were, so in this question I think we were maximizing, and then subject to the constraints were, I believe, x1 less than or equal to 4, 2x2 is less than or equal to 12, 3x1 plus 2x2 less than or equal to 18, and of course we also have the non-negativity constraints that x1, x2 were non-negative. This was the problem, and we sketched the feasible region for this problem. And now let's look at the corner points or the vertices of this feasible region. So I have a vertex at the origin, I have a vertex at 0, 6, I have a vertex at 2, 6, I have a vertex at what is that point? That point would be when x1 is 4, when x1 is 4, it is 6. Okay, so this is the point 4, 6, and then this is the point 4, 0. So these are the vertices. So what is a vertex? That's basically the intersection point of the sides of the feasible region. And we're going to define vertices more generally in the n space and so on later. But at this level, let's see how the simplex works. So simplex starts with an initialization. Okay, initialization means that it starts with a vertex. Okay, a vertex which is a CPF solution. Remember what I meant by CPF? Corner point feasible solution, right? Notice that if I look at this point here, this is a corner point, but it is not a corner point feasible. Okay, so we are talking about CPF solutions, and what? So the initialization step of simplex is it starts with a vertex. Usually it is 0, 0. Okay, usually 0, 0. The origin is a vertex. Okay, and then later we are going to see what happens when 0, 0 is not a vertex. How do we come up with a CPF solution? That's going to be later. But right now, let's say somehow we know there is a feasible corner, there is a CPF or a vertex which is a feasible solution, and the LP, the simplex starts with that solution. So at the origin, so let's say our simplex starts with 0, 0. Then what does it do? Well, then it's how many of you have taken a programming class? So then it's like an iteration. An iteration starts. Okay, it is going to ask the following question: have I achieved the optimal solution at 0, 0? So there is a condition whether I have achieved the optimal solution at 0, 0. If I have not, then I'm going to move to a adjacent corner point solution. Okay, and then I'm going to ask the same question: is it optimal? If it is not optimal, then I'm going to move to the next adjacent solution. Am I making sense? Now, two vertices are adjacent means that they are joined by a edge. There is an edge between them. Okay, in this case, edge means a boundary that connects them, right? But we're going to define edge for n space later. So how does it check whether you have achieved the optimal solution at a vertex? How do you check that? Now, first of all, let me say that if there is an optimal solution, then you know that one of the corner points will give you the optimal solution. Am I making sense? And if you suppose you have a vertex, and then you know that none of the adjacent vertices are giving you better values of z. Listen to it carefully. I'm saying, suppose I have arrived at a vertex, and then I see that if I move to any of the adjacent vertices, I don't get a better value of the objective function. Am I making sense? Then I know that wherever I arrive, that's the optimal solution. Is everybody clear? First of all, given that there is an optimal solution to the problem, I know one of the vertices will give me the optimal solution. And suppose I arrived at a vertex, and I know that none of the adjacent vertices will give me a better value of z, then I know that I have arrived at the optimal corner point solution. Is that clear to you? Is everybody clear? So let's now see how. So for this problem, let's say the initial step 0, 0. The program takes on the value 0, 0, and then it's going to check whether we have achieved the optimal solution at 0, 0. Well, how is it going to check that? Well, it has to check whether any of the adjacent vertices will give you better values of z. Okay? So then the program looks at, so what are the adjacent points to 0, 0? The adjacent point 0, 0 is either 4, 0, so let me draw that point, 4, 0, this point, or the point 6, 0, right? Sorry, 0, 6. 0, 6. Right? These are the adjacent points to the origin. The program will check whether I get a better value of z at one of these adjacent points. If I do, then I'm going to move to one of them. Am I making sense? Now, you can check that both of the adjacent solutions, adjacent vertices, give you a better value of z. Am I making sense? Look at the value of z. 0, 0 gives you the value 0. But 0, 6 or 4, 0 gives you a better value of z, right? Am I making sense? So you can either move to the adjacent vertex 4, 0 or the adjacent vertex 0, 6. Okay? But in this case, we are going to move to 0, 6 because 0, 6 gives you a better value of z than 4, 0. You agree? When you plug in 4, 0, what do you get? What's the value of z at this point? At this point, the value of z is 12. What's the value of z here? The value of z here is 30. So let's say I'm going to move to the point 0.6. Okay? Now, the program actually doesn't evaluate z. The program doesn't, the simplex really doesn't evaluate the objective function at the adjacent vertices. Okay? It doesn't really evaluate. What does it do? Well, it asks the following question. If I move toward this, what's the rate of increase in z? At what rate z increases if I move along this edge? Versus what's the rate of z? What's the rate of increase in z if I move along the other edge? Am I making sense? Can someone tell me what's the rate of z if I move along the edge between 0, 0 and 4, 0? Well, it will be, you see that 3? If I move along this edge, this guy is not there, only this is changing. So the rate of increase is what? 3. On the other hand, if I move along this edge, the vertical edge, the rate of increase would be 5. So which one is bigger? First of all, is it positive? The rate of increase is positive. If it is negative, then I wouldn't be moving. I would be staying at 0, 0, and that would be my optimal solution. But program checks that, well, if I move along the horizontal edge from 0, 0, the rate of increase in z is positive, so I get a better value of z if I move along this edge and go to the next adjacent vertex. And I also get a positive rate of increase if I move along the other edge. So both of them are valid. I can move along any one of them to get a better value of z. However, the vertical edge is giving me a better rate of increase in z. So I'm going to move along that edge. And as I move along that edge, I'm going to reach what vertex? 0, 6. So what's the value of the objective function at that point? It's 30. Am I making sense? So so what step did I do? I had the initialization, meaning that you start with a corner point solution or a vertex that is a feasible solution. 0, 0 in this case. You start with that, and then the next step is the simplex is asking, have I achieved the optimal solution? How does it check it? Well, it's going to check whether I can move along any of the edges from this point 0, 0 and see that the rate of increase in z is positive. Am I making sense? If the rate of increase in z is positive when I move along any of these edges, that means there is a better vertex, right? There is a vertex which will give me a better value of z. Am I making sense? Now, when I say rate of increase is positive, remember we are trying to maximize. That's why I want positive, right? If I wanted to minimize, then I would be moving along an edge which is going to give me a negative rate, right? Because I want to decrease, not increase the value. You guys agree with that? Is everybody following what I'm saying? Okay, so now I arrived at the point 0, 0, 6. Okay, so the now iteration goes back. Iteration is going back. So I have the point 0, 6. The simplex will check, have I achieved the optimal solution? How do I check it? Well, from the point 0, 6, I can only move along the horizontal edge which goes to the vertex 2, 6, right? Or I can go back to 0, 0, but I know 0, 0 I already know 0, 0 is a vertex where I get a smaller value of z, right? So now I can only move to the next adjacent, right? So the program will say, well, moving along this edge, does it give me a better value of z? Okay? And it will say, yes, yeah, it does give me a better value of z, so I should move to the next adjacent point, adjacent vertex. What's the value of z here? The value of z here is 36. When x1 is 2, x2 is 6, that's where I get z to be 36. Okay, I reach to this vertex, and then once again, iteration starts, right? Is this the optimal solution? Yes or no? Well, is there a better adjacent? Is there an adjacent vertex which is going to give me a better value? Well, what are the adjacent points? Adjacent points are here or here, right? I already know the adjacent point at 0, 6 is a point where I get a smaller value here, right? That's why I moved from there. So do I get a smaller or a bigger value of z here? That's the question. Well, you can check that the value of z here is, I don't know, what was that point? I think it was the point, I forgot what that point was. I think I wrote that down before somewhere. Let me quickly check what that point was. I mean, it will be the intersection of two of the boundaries. I can easily find that out, but I think I have it somewhere. Oh boy, where do I have that? Okay, so I thought I wrote it down somewhere, but I can't find it right now. Okay, so let me just try to see what that is. This would be the intersection of the vertical line with this. So if I plug in x1 to be 4, then I get 2x2 is 18 minus 12, which is 2x2 would be 6, so x2 would be 3. So this would be the 0.43, right? This would be the 0.43. And what's the value of the objective function at this point? The value of the objective function at this point is, if I plug in 4, I get 12. 12 plus 15 is what? 27. So I get the value 27. So I see that once I arrived at the point 2, 6, there aren't any adjacent vertices which will give me a better value of z. Right? Remember what I said? Once I arrived at a point, at a vertex, so that none of the adjacent vertices gives you a better value of z, that means you obtained the optimal solution. So 2, 6 will be the optimal solution. Remember, that's what we got from Excel as well, and also by using the graphical method, we got the same objective, same optimal solution. Did that make sense? So one key thing here, a couple of key things. One is the simplex method really doesn't check all the points, right? How many feasible points do I have? Lots of them. The entire region, right, contains all the feasible points. But the simplex is only checking how many points? Finite number, right? I have infinitely many feasible solutions. The simplex is only checking how many? Finitely many. Right? Of course, that finitely many could be a lot. When you talk about n-dimensional spaces, then that would be a big number of vertices. But the point is, though, I have only finitely many vertices versus infinitely many points, so I'm only checking those. And simplex goes from one vertex to an adjacent vertex. So it starts with a vertex, then it checks whether I can get a better value of z if I move along one of the edges coming out of that current vertex. If I can, I move to the next better adjacent vertex. and then I redo the same process. Okay, so it is actually an iterative process that's happening. Come to a vertex, check if it is optimal. If it is not, move to a better adjacent vertex. Once you arrive at a new vertex, do the same thing, right? And keep doing that iteration until you arrive to a vertex, so that none of the adjacent vertices are giving you any better value of z. And then you know you have arrived at the optimal solution. Is everybody clear? Is that okay? So that's the graphical view of the simplex method. So let me sort of recap what I just said. So there is the initialization step. So first of all, you have a initialization. Step. This is where you start with, for now we are going to assume that we start with the origin. If it is 3 space, we start with the origin at 3 space. If it is n space, we start with the origin of the n space. So that's the initialization process. We're going to later see what if that's not a feasible vertex. Okay, we're going to see that later. And then once you have a vertex, you check whether you have an optimal solution. So this is the next step, is the optimality test. Okay, optimality test. Optimality test is basically is the current vertex optimal. Okay, how do I check that again? I want to check whether there is an adjacent vertex which will give me a better value. So right, check. So this means check if there is an adjacent vertex that gives a better value of z. Okay, and then the next step is the iteration step. Iteration step is that basically you move to. So if the answer, so what would be the iteration? So if the answer to the optimality test is yes, I have arrived at an optimal solution, then the program stops, right? If the answer is no, it's like an if-then statement, right? In programming, if it doesn't, if no, then I do the iteration step where I move to a better adjacent vertex. Okay, move to a better adjacent vertex. Okay, and once you have that step, you are going to come up with what? Iteration step will give you a new vertex, right? And then the program goes back to which step? The program goes back to optimality test. The new vertex, is this the optimal solution? If not, go to the iteration again. Find a new adjacent vertex, right? Go back again. So this is an iteration that happens again and again until you get to that optimal solution. Did that make sense? Any questions on what I just said? Now, the reason I went over the graphical view is that it gives you some intuition on how simplex work, and as we go through the more look at the algebraically how this method works, you will better understand how the algebra works. Okay, so let's now think about how the simplex works algebraically. Any questions you guys have for me right now? Okay, so let me start explaining things by using an example, and I'm going to use the same example. Remember, we looked at this, maximize z equals to 3x1 plus 5x2 subject to x1 less than or equal to 4, 2x2 is less than or equal to 12, 3x1 plus 2x2 is less than or equal to 18, and x1 is greater than 0, x2 is greater or equal to 0. So these are our constraints. Okay. Remember, we are working with the standard LP. Whatever problem you have, convert it to the standard LP, and then you're going to follow what I'm doing. Okay. Now, what will be the first step? We are going to write down. This is the standard LP, right? This is the standard form. This is the standard LP. Standard LP means all variables are non-negative and all the inequalities are less than or equal to. Now once I have that, then I'm going to, the next step is to write down the select form, what we call the select form of the LP. So what's the select form of this LP? Well, the objective function doesn't change. It is still maximize z, which is 3x1 plus 5x2, and for the first inequality we are going to see x1 is less than 4. So what I'm going to do is I'm going to introduce a new variable there, and I'm going to call that let me say subject to x1 plus 0. So far I have plus 0 x2 on the left hand side of the first constraint, and what I'm going to do is I'm going to add a slack variable, which, because I already have x1, x2, I'm going to use a new variable x3 and make the inequality a equality. Okay. So basically, what is x3? x3 is 4 minus x1, right? x3 is basically 4 minus x1. Should x3 be non-negative, or it could be negative? Remember, x1 is less than 4. So if x3 is 4 minus x1, then we want x3 to be what? Non-negative. Right? Think about this. If I have x1 less than 4, I need to add a positive number to make it equal to 4, right? If x1 is less than 4, I need to add something positive to make it equal to 4. So that's what I did. So x3 is the slack variable. And then for the second constraint, we do the same thing. Second one, I have 0x1 plus 2x2 plus, and I'm going to add a new slack variable x4, and to make it I'm going to replace the inequality with equality. And the third one, I have 3x1 plus 2x2 plus x5 equals to 18. And all the variables are non-negative: x1, x2, x3, x4, x5. They are all non-negative. And these two collections of constraints are equivalent. Okay, they are equivalent. Okay, so is everybody clear how I'm getting this select form? I'm adding a new variable on the left-hand side of each inequality and replacing the inequalities by equalities. Okay. Any questions? Anyone on that? Now, let me just point out one thing here, which is generally what we are doing is the following, in a general sense. Generally, we have a problem like, so generally we have a standard LP looks like what? Maximize Z, and this is C transpose times X, right? What is X here? X is the vector of decision variables, x1, x2, up to xn, right? C transpose represents the vector of which consists of the coefficients of the objective function. Maximize Z, and then what's the subject to what constraint? Subject to the constraint, the coefficient matrix A multiplied by X is less than or equal to the vector B consists of the right-hand side numbers, right? You remember that? In our problem, B is what? 4, 12, and 18, right? 4, 12, and 18? Remember we talked about the matrix form of the LP, right? You have to remember what that matrix form is and how does it associate with the standard LP, right? And then what is B? B is the right-hand side of B consists of the right-hand sides of the constraints, right? And then, of course, we have that X is non-negative, right? That's the standard LP. What is the select form? What is the corresponding select form? We are saying the select form is basically, well, you don't change the objective function, but you are going to change something here. What are we changing here? Well, with AX, what are you adding? With AX, what are you adding? You're adding a select variable. So let's write XS will denote the vector of select variables. For each functional constraint, you have a select variable, right? For each functional constraint, you have a select variable. And XS is the collection of all, it's the vector of the select variables. And then that's equals to B, right? And what are the constraints? Well, we want X to be non-negative. We also want XS to be non-negative, right? That's what we did. Any questions on what I just said? Is everybody okay? So that's what we are doing with the select variables. So we are converting the inequalities into equalities, okay, by introducing these select variables. Okay, now we are going to I'm going to introduce to you now what we call a dictionary, okay? And so what is a dictionary? A dictionary. Okay, so what is a dictionary? Well, a dictionary, basically what the initial dictionary will be like this. Let me go back to the example that I had. Let's look at the Slack form of our example. And what I'm going to do here is I'm going to solve for the slack variables. Okay? So solve for the slack variables. So what I'm going to get is x3 is equal to, let me write it a bit here, x3 would be equal to 4 minus x1 plus 0 x2 x4 would be 12 minus 0 x1 plus 2 x2 x5 would be 18 minus 3 x1 plus 5 x2. Okay, so what did I do? I went, so remember the slack variables, we wrote down the slack form. Once I had the slack form from each one, so from the first one I solved for x3, second one solved for x4, third one solved for x5, right? So if I do that, I am going to end up with this, okay? And then I'm going to write a horizontal line underneath, and then I'm going to write down z, and z, I'm going to write, remember what was z? Z is 3x1 plus 5x2, okay? And I am going to add 0 here because it doesn't change anything. Okay, is everybody done writing it down? So this is our initial dictionary. Now we are going to operate, we are going to do some sort of operation on the dictionary to come up with new dictionaries, okay? And when I have a dictionary, the left-hand side of the equalities that I have here, the left-hand sides, the variables on the left-hand side will be called basic variables. So these variables that I have, I'm going to call them basic variables. Okay? The variables on the right-hand side, they will be called non-basic variables, or sometimes they are called independent variables. Am I making sense? Is everybody okay with that? Now, I'm not going to introduce to you the other operations today, but imagine that you do some sort of operation on the dictionary, you come up with another dictionary, okay? And then you're going to, basically it's going to change the basic and non-basic variables. It's going to change. So when you do the operation, one of the non-basic will enter the basic set, and one of the basic variable will become a non-basic variable when you do some operations. I'm going to introduce that later. But my point is, think of a dictionary. This is a way for us to, this is like a data structure. Like this is if you want to write down a computer program, you have to store information, right? You need a data structure to do that. This is a data structure, okay? And also this is a convenient way for us to represent solutions. Each dictionary is associated with a vertex solution. How? Notice that if I set the non-basic variables equal to 0, and then I solve for the basic variables, I get a solution. Okay? And that solution will correspond to a CPF or a vertex solution. Is that clear? So for example here, now here if I set x1, x2 to 0, right? Set non-basic, well, let me do it later, okay? We don't have much time left here. But let me, so what I'm saying is that each dictionary is associated with a solution, and when I write the number 0 here for z, what's the solution now? The solution now is x1, x2 are 0, and then what is x3? 4, x4 is 12, x5 is 18, and what's the associated value of z? The associated value of z is 0, right? So it is so nice that anytime you come up with a new dictionary, you get a new solution, and the associated value of z will be written right here as you do the operations. Am I making sense? Is everybody clear? So this is so nice that way, and it is so nice that you always set the right hand side to 0, and then you solve. It's easy to solve for the left hand side. Now, one question that I want to ask: suppose one of the numbers, suppose you have a dictionary, and one of the numbers here is negative. What does it tell you? What does it tell you? What's the associated solution then? The associated solution will have some negative numbers, right? But remember, all the variables are non-negative. So if you get a negative, that means you got an infeasible solution, right? All right, so we're going to move from there. Right now, just remember what is given a LP in standard form. How do you write down the select form, and how do you write down the initial dictionary? Okay, and then we're going to move from there.